Hi. So we're not exactly done with question 8, right? There's one small part that I left out, which is this. Right? If the angle theta was very small, calculate the pitch of the helix, right? So it's not an issue because we know that the horizontal component here, right, is dependent on theta. So if theta was very, very small, your horizontal velocity would get ever closer to the original 7.0 10 to the power 6, right? Meters per second. So if, however, right, and the important point to note is that the period of doing a cycle is not changed, right? Because if you look at the equation here, that I have over here, notice that the velocity in the vertical component, it does not play a part in the period, right? So if the vertical component doesn't play a part in the period, the initial velocity v also does not play a part in the period. So the period stays constant, which means that you can calculate the pitch purely depending on theta. And when theta is very, very small, cosine theta is equals to 1, as demonstrated here. So all you have to do is multiply it together and you get this value. Alright? So moving on, we are going to talk about question 9. Question 9 is a challenging one. Let's bring all of them to the same page. Make our lives easier. What is happening? Maybe not. Alright, so let's see what's happening here. So we have okay, the magnitude of the field strength B at a point is given by this. Okay, actually, in the current H2 syllabus, you are given the equation as mu naught I over 2 pi r. This essentially is mu naught divided by 2 pi. Okay, this value that you see here, that they give to you, is essentially mu naught divided by 2 pi. So 2.0 10 to the power minus 7 is mu naught divided by 2 pi. Right? Shouldn't come as a surprise because mu naught is given as 4 pi times 10 to the power of minus 7. Right? So mu naught is 4 pi times 10 to the power minus 7. So if you take mu naught divided by 2 pi, you essentially just get 2 times 10 to the power minus 7, which is the value that you have over here. Next, 3 long parallel conductors carry currents of 2.0. The figure above is the end view of the conductor. That means the currents are coming towards us. Given that A is equals to 1 cm, determine the magnetic direction of the field at A, C, and D. Now, this is a really, really painful question to do because it is repetitive. However, it is important to check your understanding on addition of vectors. So let's take it step by step. There's wire R over here. There's wire P below and wire Q over here. Q is the furthest. So let's do it step by step. All right, let's copy the diagram over here. So R. Let's look at R first, right? Let's use R in black. It is a certain distance away here. So using your right hand rule, right hand grip rule, the B field due to R must be perpendicular to the previous. and it should be pointing down this way. So this is the BQ to R. Okay, let's look at P now. Let's complete the square. Oops, P is here. So again, we dot it back to where A is. A is over here. Using your right hand rule, right hand grip rule, the BQ due to P must point perpendicular to it, to the radius, and point this way. I think that the magnitude for R and P's are the same. Is that correct? Yes, that must be correct because B due to R is 2 times 10 to the power minus 7. The current value is 2 and the distance is 0.01. The BQ due to P happens to have exactly the same working. Okay, but this does not mean these two vectors are the same because remember it's a vector, they point in different directions, we have to sum it up. Next, we have Q. Now Q is an interesting feature because it is pretty far away. Oh, I've made a mistake, sorry, my bad. Right, this is A, this distance here is A, which is not 0.01. Right, this distance here is A. Right, but their distance, what's this distance over here? If this is A, over here, and A over here, the distance there should be square root 2A, right? Sorry, square root 2A. Right? So this should be the distance of square root 2. Right. So let's look at Q now. Q is the distance of A, 2 A's, and a third A away. Wow, this is far. So using your right hand grip rule, if this is the radius to point A, it should be perpendicular to it, so it should be BQ to Q. Okay. And B due to Q has the same currents, 7, currents 2. The distance is 3A. So let's leave it as A. Right, so now we have to add these three vectors together. We know that the angle here is 45 degrees. So the resultant B at A is BR cosine 45 degrees plus BP also cosine 45 degrees, right, because this is also 45 degrees, and add BQ, sorry. So let's do it. What is it? Taking out the common factors, we have 2 times 10 to the power minus 7. Each of them has a current of 2. The rest will be 1 over, and this whole thing over A. It'll be 1 over square root 2 here, plus 1 over square root 2 here, plus 1 over 3. Right? So now just plug in the value for A. A is essentially just 0.01. You have a whole bunch of numbers, type it in, and you should get your solution. Right? Let's look at what we have. It's long. 53.3 microtesla to the bottom of the page. Yep. Should be correct. Okay. So notice the solution given, instead of doing this twice, right? Instead of doing this twice, they used this. Right? It says 2 multiplied by. Okay. Same thing, no issue. We are then asked to find the B field at C. B field at C is actually interesting. Let's repeat the same things that we have done. R here, and the distance A away. So using your right hand grip rule, the B field due to R points this way. Okay. P is the distance A away, pointing out the right hand grip rule, the B field due to P points to the left. And these two values are the same, right? Equal distance, equal in current. These two will cancel each other. So we don't really have to care about them. We will then completely. So all we have to do is to care about the B field due to Q, distance of A, another distance of A, and this is Q. The B field due to Q points down, so the B due to Q. So this is actually, the B field at C is actually pretty easy. It's just 2 times 10 to the power minus 7. Current of 2 ampere. Distance of A, or 2A. So 2 and 2 cancels out. We have 2 times 10 to the power minus 7. A is 0.01. The answer should be 2.0 10 to the power minus 5. Should be correct. Let's check it out. And I use some mental sums. Please forgive me if I'm wrong. There you go. BC is 2 times 10 to the power minus 5 towards the bottom of the page. Right. Let's look at the third one. The B field at D. B field at D. Let's try. So let's again repeat what we've done again. 2R. Draw towards D. The B field using a right hand grid rule points perpendicularly out this way. Oops, not very perpendicular. So this is the B field due to R. Due to P, P is down here. Let's check it. Perpendicular to the radius. This way. Magnitude is the same as R. Right. And next is Q. Q is also a distance of A away. Oh, so all three of them are distance of A away, so that's nice. That saves us a lot on the working, so that's PQ. Right, so let's look at it. BP and BR, they are symmetric in the left and right directions because they are both 45 degrees away from the vertical. Oops. Let's draw that back in due to the great one is PR. Right, so let's calculate it then. BP equals to 2 times 10 to the power minus 7 as given by the question. The current is 2. Distance is A, so that's 0.01. Right? So this gives me 4 times 10 to the power minus 7. And the magnitude of BR is the same. Right? BR magnitude is equals to BP. And it's also the same as BQ. Like all of them have the same magnitude of 4 times 10 to the power minus 7. Of course, if you give it as 4.0. So all we have to do now is to decide whether the upward pointing vectors, which is BP and BR, right, they have, oops, this should be red, right, this is the one due to P, this should be black, this is the one due to P. Right. Just need to decide whether upward pointing vectors same. So cut the story short. So 2 times BP cosine 45 degrees. Find this value. You can compare this value that we have here with 4 times 10 upon S, which is larger. Okay. Let's see. Here we have, it's actually equal in nature. Oh, in the values. Is that surprising? Maybe not. So, since it's the same, the resultant field at D must be 0. And that's that.